Let's look at non-contiguous VLSM. You can think of non-contiguous variable length subnet masking in terms of block sizes and the host or subnets required. Remember, a block's always the lowest bit that belongs to the subnet bits. If we look at it in a byte table, or you can also find it by subtracting the subnet mask from 256. Let's look at the following example byte table. Under normal class full rules, not CIDR, but class full, we would start subnetting on 2 bits, and we would end on 6 bits, the reason being we don't want to turn them all on or all off. If that were the case, I would just add the 128 to the 64, and that would give me a mask of 192. I would add the 128 to the 64 to the 32, and that would give me a mask of 224, and so forth, all the way down 240, 248, 252, just adding the consecutive values up to obtain or find the subnet mask. If I do that, that also gives me the block because I can simply subtract this from 256 to achieve the block, or take a look at your byte table. It's the lowest bit being used for subnetting, so in this case 64. Lowest bit being used for subnetting, in this case 32. 16, 8, 4, and so on. So if I know that, I can use that information to generate a table. And if we were going to apply Vlsm to a Class C network, we would of course start with CIDR 24, right? In a normal Class C network, 24 bits, or 3 bytes or octets, are used for the network portion. So my mask would be 255.255.255.0. So that's if we're not subnetting anything, and I'm using the last octet in all 8 bits for the host, of course. So let's say that we were to further subnet that Class C address. If I did CIDR 26, based on the, on the table up here, there's 2 additional bits, my mask would be 192, right? If I added 3 bits, 224. If I added 4 bits, 240. 5 bits, 248. And 6 bits, 252. If I did that, I can apply my formula here and figure out the number of subnets I get by adding each of those bits in. Remember that when we were doing classful IP addressing? I'll bring up the table here and the formulas we used. So it's these basic 5 combinations here of bits based on our formula. 2, 6, 14, 30, and 62 subnets respectively, based on using 2, 3, 4, 5, and 6 bits. Okay, so I'm going to go ahead and put that in my table. These are the subnets that I want. Notice there's an inverse relationship. Here I start at 2 and end at 62. Here I start at 62 and end at 2. Look at my formulas. The same thing applies. 2 bits, 6 bits, 262. And then they flip, or they invert as we go down. So now that I'm using 6 bits and 2 bits, it's 62 subnets and 2 hosts. So we put that into our table for subnets and hosts, and then of course the block value might help us as well. 64, 32, 16, 8, and 4, and that'll help us in planning our network address. So you might want to either memorize or construct a table like this to help you if you're going to do non-contiguous variable length subnet masking. Now, what we want to do is we would start out and just basically we want to figure out the exact number of hosts that we need for each subnet. And this will try to help us avoid wasting, needlessly wasting IP addresses, which if we used classful IP subnetting, we would have to do. We would be wasting a lot more IPs than we would be doing with non-contiguous Vlsm. So really, this is all that's important: 11, 19, 23, 5, 2, whatever the number of hosts are that I need. Assess the situation, figure that out, put that into your table. And so I know I need 8 different subnets. I figured out the number of hosts I need per subnet. All I have to do now is figure out the right combination of CIDR, mask, block, and the actual host I'd be provided. If I need 11, how can I fit that in there? How can I fit, well, there is no 11, but the closest match to that, what would accommodate it without wasting too many IP addresses, would be 14 here. So I know that my CIDR would be /28, my mask 240, my subnet's 14, my host 14, and my block 16. Okay? And so that's what we've done here. We figured that out. And that's how we would set it up with non-contiguous VLSM. Let's look at the next one, 19. I need 19 hosts. So looking at this table, what's the combination? And if you want to apply your formulas, remember we're just getting it from applying these formulas here. But looking at the next combination, for 19, again, there's no exact match for that, but the closest I can get without wasting too many IPs would be this one here that provides 30 hosts. So that would be CIDR 27, mask 224, block 32, and the number of hosts provided would be 30. And then I would just keep going. 23, I could apply the same. 5, I don't want to waste too many. So what is closest to my 5 would actually be CIDR 29, right? In this case, 6 hosts. And then finally here for the 2 value, for the rest of my networks, again, here's an exact match right here in terms of number of hosts. So CIDR 30 and a block of 4. Once I have this, I would fill out this table, I'd calculate or assess my situation, figure out how many hosts I needed per subnet. I would plan that out. Now I'm ready to actually position them or place them. And what I would do is develop a chart, or come up with a chart to fit them in non-contiguously, so to speak. And what you want to do is start with the largest blocks first. And remember, you have to start with the block size or a multiple of that block at least, a multiple thereof, because that's what the block is. It's the base multiple on which you build your subnets. So, it's easy to fit small ones. You can tuck them in places where, there's just some range of IPs available. But, the reason you want to start with the larger blocks first is it's harder to fit them in. It's harder to find a spot for them. What's a typical, in the last I had, I only have 256 possible values here, 0 to 256. So let's look at positioning them or placing them. What's my largest block? My largest block would be 23. There's 23 hosts here, so network 3 is really the one that I want to place first. Now, I have to build that on a block value of 32. So I have to at least start at 32 or a multiple thereof. Couldn't start at like 15 or 7 or something like that. So N3 is the first one that I really want to position or that I want to place. And I can look at that and, I can start on it. Like I said, I can start on the block value, or if I wanted to, I could start on a multiple of it. So if I did that and wanted to start at 64, I could get my 32 addresses here in this address space. And this is how I could assign my IP addresses. My actual Vlsm IPs would be here in that block. And then what's the next largest one? N2 and N1 are the next 2 largest blocks. And they're based on, this one, N2 is based on 32, and N1 is based on 16. So let's look at N2. We have, let me see, there's N3, there's N2, and here's a range of 32 here. Started that on, and then I have N1. N1's based on 16. And so I want to start that at 16. And 4 is based on 8. Remember the block value is 8 up here. So this will be my range. And then the remaining networks that I have are, fairly small. Based on a block value, I could just tuck them in anywhere I can find, something based on their block value, using that as a base multiple. So like for network 4, a block value of 8, I can just tuck him in over here. He starts at 8. And the rest of these are just 2. They're really small. Only a block value of 4. And again, I can just tuck them in wherever I can find a spot. So networks 5, 6, and 7 and 8, let's see where we can tuck those in. And over here, I can do 100 and 104 and 108 and 112. And if I did that, good grief, I'm wasting far fewer. If this were classful IP addressing without Vlsm, without CIDR, I wouldn't be able to do this. I'd actually be limited to just 2 subnets of 62 hosts each. It's 62 hosts each. But in this case, I have many more options. It's definitely more options here. Let's take a look at variable length subnet masking, or VLSM. And there's contiguous and non-contiguous forms of that. So we'll look at the contiguous version of it first. But basically, the need for VLSM comes from the fact that classful IP addressing wastes a lot of IP addresses. And again, recently we've had an IP-apocalypse with IP version 4. And don't panic, that doesn't mean, a lot of universities and private organizations and companies and things will still continue to use IP version 4 for years to come. Because, again, they can do whatever they want behind their routers and their firewalls on their own private networks. But as far as the internet is concerned, we're definitely moving, we have to move into IP version 6 now to have enough IP addresses and things to go around. But still, that doesn't mean we want to waste IP addresses. So using classless interdomain routing, CIDR notation, and variable length subnet masking or Vlsm are ways to avoid wasting those precious IP version 4 addresses when we do decide to use them. And what you can think of it as is basically splitting subnets into a binary tree, essentially like subnetting a subnet. And this tree will fork into subnetting a subnet of a subnet. And now each time you do this, remember, just like in classical IP addressing, RFC states that certain bits have to be stuck on or stuck off for class A, B, and C. Well, the same rule will apply when you use Vlsm. So if we were to look at a table, the standard classful IP version 4 addresses here, class A, class B, class C, would of course have the CIDR notation 8, 16, and 24 corresponding to the network bits used for those classes of addresses. Now let's look at a class B example here. We'll kind of pick it apart. So remember that, again, by RFC, since 2 bits are stuck, the range that you can have, the first bit is stuck on, the 128-bit and the 64-bit is stuck off. So that means we could only have something in the range of 128 to 191. Remember that our subnet mask, that's 16 bits for the network and a remaining 16 bits for the hosts. That means our CIDR notation would be /16. If we apply our formula, 2 to the power of x minus 2, we would get 65,534 hosts with 16 bits. And remember that the precedence is different. All right. Here I apply the exponent and I raise it to the power of 2 before I subtract the 2. But it's watch the parentheses of the precedence there. Here I'm subtracting 2 from the number of bits and then I'm applying the exponent. So in this case that would be 2 to the power of 14 or 16,384 networks. So that's just a normal class B address. And let's look at using contiguous Vlsm and subnetting that in a little bit different way than what we're used to, according to the classful methods. So if one single class B network gives us 65,534 host addresses, and this would be the CIDR notation, if we were to split that in half on the 128-bit, take a look at this byte table down here. Here's our 8 bits and our byte. If we were to use Vlsm on this bit here, we could flip this bit on and off. Now, don't panic. I know that with classful IP addressing, the rules that we apply are that we can't do that. We can't really subnet on a single bit because we can't turn all the bits on or all the bits off as far as our subnet bits. So we'd need like a minimum of 2. But this is not classful IP addressing. This is variable length subnet masking, Vlsm, and classless interdomain routing, CIDR. So we're going to bend those rules. And in this case, now we're just going to subnet on one bit. It's either going to be all on or all off. Flip it on, flip it off. If we did that, we could take these 65,534 possible host addresses and split them up into 2 chunks that could handle about 32,000 hosts per subnet. So we'll use the subscript values, but N1, CIDR 17, would hold the first 32,000, and that's with the 128-bit turned off. And N2, notice the subscript value, would hold the next 32,000, and that's with the 128-bit turned on. Okay, so we're something different here now. We're bending the rules using CIDR and Vlsm. And if we were to look at that in a byte table, again, here's how it would look: bit turned off, bit turned on. Now that would give us, again, that's still a pretty large broadcast domain, and most organizations are probably going to have subnets that are smaller than that to contain the broadcast traffic. That's just a huge number of devices trying to share the same network or the same subnet. So for the purpose of being contiguous or organizational unity, we might want to put everything on a single class B, but we would certainly want to subnet that further. And so we could subnet that subnet of a subnet, and we could just keep going. And if I wanted to do that, think back and remember, we can, if using CIDR, and right now I'm currently using 17 bits, so the first 16 are the network part, and then this 1 bit here in the third octet or the third byte is, that's my subnet bit that I'm flipping on and off. If I wanted to, I could further subdivide that. Let's say that I want to do in the next range, on network 2, I want to further subdivide that or further subnet that. So I could tree off. And if I did that, then what I would do is I would leave the 128-bit on, right? It would be stuck on or flipped on, and I could add another 4 bits. And think back to our formula. Remember our formulas for calculating the number of hosts and subnets and so forth? Let's say that I wanted to get 14 subnets out of that address. I'd need 4 more bits, just applying my formula. So if I come over here, if I were to do this, the 128-bit stuck on, I could use, in this case, I know you can't use the network address and classical IP addressing, but in this case I could actually just use the 128-bit. That would be my first network. So although according to the formula, in classical IP addressing I'd have 14 subnets, I could actually get 15 out of this bit. Let's look at the very first one here. So 128 bits turned on, and that's going to be what, my very first subnet of my subnet or my network. So what's the next possible value? If I decide to subnet on 4 bits, right, then this becomes the first subnet, and then I add another 4 bits, so a total of 5, and that becomes the subnets in my subnet that will be eventually a subnet of my network. So if that's the case, then the next lowest value I can come up with is if I turn the 8-bit on, and that gives me 136. The next lowest value is if I turn everything off and turn the 16-bit on. That's 144. The next lowest value, if I turn, both of these on, the 8 and the 16, in this case, that'll give me the 152 here. And then if I turn both of these off and turn the 32-bit on, that would give me 160. So just manipulating these 4 bits and going through the bit values there, you can see that these are the 14 possible subnets plus the original subnet here when I applied my Vlsm to that standard class B network. And as we progress, as we move further, each time I move into a subnet of a subnet, a greater number of bits get stuck. So I need to kind of keep an eye on my byte table and watch the bits that I'm turning on and turning off, or what gets stuck and what's not stuck. So if we were to apply this, how many, looking at these bits here, 5 bits total for the subnetting, and how many left for the host? Well, that only leaves 3 bits left for the hosts. Now this is the 3rd octet, or the 3rd byte, so the 4th byte, or the 4th octet, there's an additional 8 bits. And were I to combine them, that'll give me a total of 11 bits there for the hosts. And again, if we were to apply our formula, think about it. 2 to the power of x minus 2, or 2 to the power of 4 minus 2, there's our 14 subnets, plus the original subnet, so 15. And our hosts, 2 to the power of x minus 2, so 11 bits, 2 to the power of 11, gives us about 2,046 hosts for each of those subnets. Now what does the CIDR look like? It's no longer CIDR 17, but we've added 4 more bits, so it will be CIDR 21. And then what's the block size? Well, remember the block size is the lowest bit. So if you look at the table, I'm subnetting these 4 bits of this subnet, 5 bits altogether, but the lowest bit is 8. So there's my block value. And then let's look at what, kind of what we have achieved here, or let's look at what the actual subnets would be. So network 1, in other words, the subnet of the subnet, the first subnet of subnet 2, because we first split the address into 2 subnets up here, remember, 128-bit off, 128-bit on, and we're subnetting this subnet, the 128-bit on. I'm trying to say this in the least confusing way possible. I'm not trying to overuse the word subnetting, but that's what we're doing. We're subnetting a subnet of a subnet or network. So in this case, that second subnet, right, the 128-bit turned on, the first subnet of that, when I add the 4 additional bits to the one I was already using, remember CIDR 21, so now it's a total of 5 bits, would be this, the 128. The next subnet, 136, 144, 152, 160. Remember the block is the base multiple, so I'm just adding 8. And as I add 8, that gives me my subnets as I go all the way down. And again, I'll look at the byte table. Why? Look, there's our block value right there, just adding 8 as we go. Okay. And then that would give me, again, that's probably more, 2046 hosts is probably way more, than I want on a typical subnet, and typical broadcast domain or a network. So I may want to further subdivide. In other words, I may want to subnet a subnet of a subnet of a network. If I decide to do that, of these 15 subnets, if I wanted to break them up a little bit further, I could approximate, combining them into like a bunch of smaller Class C networks, aggregating them or aggregation. So if I pick the last subnet of the previous stage, remember that was, we used I think it was a value of 240, yeah, right here, based on our block value. Let's say that we want to further subnet that, and I wanted to get 8 more subnets. So remember that I split the network into 2 subnets. I took the last subnet, the 128-bit, I split that into an additional 14 subnets. And now I'm going to take the last subnet of the subnet of the subnet of the network and subnet that. Oh my gosh. Yeah, I know. Maybe it's just easier if you read it. I don't know. But there is a method to the madness, so there's some logic here. So to get 8 more subnets, we want to add 3 additional bits for the subnetting. And if I do that, basically I end up subnetting the entire third octet, and that only leaves the last byte, or the last octet, the fourth one, for host bits. But think about it, that's like a Class C, isn't it? I mean, I'm Class B, but if you see CIDR 24, well, CIDR 24 in a classful IP situation, that you would look at that and you would assume that was a Class C subnet mask, right? 255.255.255.0. However, in this case, it's a Class B, and we're just using Vlsm. So if I were to do that, look at the consecutive bits that have now become stuck as we kind of move through it. In other words, going through this, I had to turn the 128-bit on, and then I had to turn the 64-bit on, and the 32-bit on, and the 16-bit on, and the 8-bit on. Okay, and then if I have all of these, then that's the point. That 240 is where I have to actually start subnetting. Okay, so total of 5 bits now become stuck if that's my block value. These bits are all stuck on here. And so that determines, that's going to kind of determine where I have to start my next range. So to sum things up, again, let's take a look at it. Our subnet mask would look like a normal Class C, although it's a Class B. Our CIDR notation looks like a Class C, but it's not. It's a Class B. Our block size is 1. A little different, but that's because we're using an entire octet, right? The whole third byte we've decided to subnet on, all 8 bits of it. So because of that, just like a Class C network, that only leaves us the last byte, the last octet, 8 bits. That means we get 254 hosts per subnet. And the number of subnets of our subnet of our subnet of our subnet of our network is going to be 8. Why? 2 to the power of x equals 2 to the power of 3. The amount of bits that we're applying here. And why? Because look at our formula. Now, I don't have to subtract the 2 because it's Vlsm. So in this case, I'm actually getting 8 subnets. Remember, we're bending, kind of gender bending or bending the the classful rules here. So I have what I need if I choose to use those 3 additional bits on that octet. And basically what I would end up with then is, okay, the first subnet of the 15th or last subnet of the second subnet of the network would be 157.54.248. Okay, and why 248? Again, let's go back and look at the byte table. It's going to be all of these bits turned on here, and I have to, if I switch all of these on, that's actually, a mask value, but based on the block, okay, 248. And then if my block is 1, I'm just going to, from this point on, these have to be all stuck on, but 1, 2, 3, 4, 5, 6, 7. And that's all we're doing here. So the first, second, third, fourth, fifth, sixth, seventh, and 8th subnets, respectively, will simply go up by 1 based on the block value. 248, 249, 250, 251, 252, 253, 254, and then the last one here, 255. Okay, that's contiguous VLSM. Let's look at another example. We'll make up a fictitious company. Baby Got Back, manufacturer of designer clothing. They have 12 office locations requiring separate networks. Let's use variable length subnet masking to conserve IP addresses and combine discontiguous subnets into one Class C network address. The locations have hosts as follows. And again, we want to focus on or gravitate towards the larger number. 4, 7, 13, 6, 2, 17, 19, 7, and 2, 26, 2, 30. Here are all the different locations or different towns and cities for Baby Got Back. So I'd fill out my chart using my formula if I need to calculate how many hosts and how many subnets I get based on how many bits I'm using. And I could fill in the CIDR notation, the mask, the subnets, and the block value just like we did before. So applying that, I'll go ahead and fill out my chart. And I'll start with network 1. And we'll just go down in order, sequentially by location. So the first network, I need 4 hosts. That's going to be CIDR 29. Okay, and again, we're assuming this is going to be on a Class C address. So that tells me the mask, the host, the block value. That'll accommodate exactly 6 hosts. So 2 extra there, but that's the closest size where I can fit it. And that tells me that everything I need as far as the block value, the CIDR notation, and the mask. 7, in this case, I'll need a CIDR 28. And that'll give me 14 hosts. 13, again, same thing. Closest match is going to be 14 hosts, which is a block value of 16. The next one, 4, well, 6, a little bit overkill, but block value of 8. And I just keep going all the way down. The most important ones here are my 4 largest, and that's going to be the 30, the 26, the 19, and the 17. Okay. These guys are going to require, I want to position them first. I need to plan this carefully. You'll notice my block size here, 32 and 32 and 32 and 32. So those are going to be the hardest to fit because remember, it has to either start at 32, I'm using the block value, or it has to be based on a multiple thereof. Okay, so I want to go ahead and position this in my chart. So really, I'd want to start, like I said, with the 32 blocks. So either network 12, network 10, network 7, or network 6. So let's look at networks 6 and 7 and 10 and 12. So I would start out 6, I'd put him in this 32 here. Then network 7, I'd put him in the 64 block. That'll accommodate or fit the 32 addresses, the 32 hosts that I need, or based on my multiple, the 30 hosts that I need, minus the network and the broadcast. Then the next 2 networks I had were network 10 and network 12. Again, based on a block value of 32, I need to accommodate 30 hosts plus a network and a broadcast. So 10, I can start him at 96. That's based on a multiple of 32. And then for 12, I can start him at 128. And this is just, the way I did this table or the chart, it's just going over into the next column, but it'd be from the 128 here, all the way down. Okay, so those are my 4 largest. And then once I fit those in, I can take the smaller ones and kind of fit them in between the larger chunks or the larger block values. So having taken care of the 4 largest, what's the next largest block I have? I took care of the 32. Let me take care of the 16 block. So it's network 2, network 3, and network 8. Okay, let's see where we would position that. Network 2, I can start it at 16. That's the block value and multiple. Network 6, or excuse me, network 3. It was network 3. Now I'm out of, because of the 32 blocks and fitting all these guys in, I'm out of addresses. So I'm fine. I can put N3 here, but I just need to make sure that it's still based on a multiple of its block value. Remember, N3 has a block value of 16. No problem. I can position it right here. Just need to make sure it's based on a multiple of 16. So once I put N3 right there, 176. And what are my next block values? In this case at 16, I had network 8. So again, I have to go find a spot for network 8. And I can position that. After the 176, I can start at network 8 at the 192 there. Okay, so I took care of the block, 32 block, my largest, took care of 16, my second largest. Now what's my next largest block? That's going to be 8. So I would want to position those or place those now. So that's going to be network 1 and network 4. And let's go look at our, and again, the smaller it gets, the easier it is to squeeze them in. So network 1 and network 4, based on a block value of 8. And I'll put network 1 here at 200, and network 4 here at 208. And again, as long as it's based on the block or a multiple thereof. And then finally, the last one I need to take care of are my 4s. So that's going to be network 5 and network 9 and also network 11. I could probably squeeze those in anywhere. So 5, 9, and 11, and here's 5 and 9 and 11. I can just throw those in. I'm actually wasting a few IPs. I mean, I could squeeze some in at the beginning or in the middle of some others there if I wanted to, but I don't really need to. I've still got plenty left over here. And again, I'm wasting far less IP addresses than I would be wasting if this were, I mean, here I can accommodate all these on one single network using Vlsm and CIDR. Whereas if this were classful IP addressing, I would need several Class C networks to try to accommodate this range of subnets.